Hello there! Today we are talking about Newton's first law. Now, a quick preface to this video. We've been having some technical issues today, so we'll see how this goes, but if I have to pause things or if it says the page is unresponsive, then we might have to take a little bit of a moment here. So we'll see how this goes, but if it says the page is unresponsive, fear not, there are solutions, but that might be something that happens. Okay, today we are talking about Newton's first law, and let's just start with a quick definition of Newton's first law. Newton's first law says that an object at rest stays at rest and an object in motion stays in motion and I'm going to add some words here. So you've heard an object at rest stays at rest and an object in motion stays in motion. Whoa. You can do it. You can do it. You can load. You can make it happen. I know it's a lot, but I believe in you. Okay, here we go. An object at rest stays at rest. An object in motion stays in motion. And then I'm adding extra words here. At a constant speed. In try again. At a constant speed in a straight line. Oh gosh, we're just going to leave it. We're leaving. That says A. That's the letter A. In a straight line. Unless acted on by an outside force. Newton's first law says an object at rest stays at rest, and an object in motion stays in motion at a constant speed in a straight line unless acted on by an outside force. Whew, that is hefty. Most of you know Newton's first law is an object in motion stays in motion. But you'll see that Newton's first law has a little bit more heft to it when we do it in our physics class and when we talk about it in our physics class. And that's because there are a few things here that we really want to be very specific with our words about. Let's talk a little bit about Newton's first law. Now, we are starting today a new unit, and this new unit is about forces and Newton's laws. Now, in previous units, like in our last unit, all that we've done so far has been describing motion. We talk about the motion that is happening. But what we haven't talked about is we haven't talked about why that motion happens. What forces cause it to happen? What forces cause it to not happen? Those kinds of things. And so, oh, wow, speeding up my browsing. That sounds fun. And so, what we're going to talk about today is we're going to talk about, and for the rest of this unit, is why motion happens the way that it happens. Why does motion happen? And we start with Newton's first law. Now, long ago, back in the day, Aristotle, the great Greek philosopher, sorry I'm making this bigger because I'm just going to talk to you, I'm not going to write stuff down for a second. Aristotle, the great Greek philosopher, was looking around the world and he was making observations about things. And as he was making observations about things, he started asking questions about, okay, what makes stuff move? First, he was like, okay, it's plenty good to describe motion, but what actually makes motion happen? And here's what Aristotle said, Aristotle said, it doesn't seem that motion is a natural thing. He said, I got a jar of paper clips. If I have my jar of paper clips sitting right here, well, this jar of paper clips isn't just going to start moving on its own. That would not be natural. That would be weird. Jars of paper clips don't just start moving. And even inside there, the individual paper clips, they won't just start moving on their own unless something causes them to move. So Aristotle said, if you want something to move, you have to put an outside force on it. And that was Aristotle's idea. He said all motion requires an outside force. Except then, they came across a big issue here because everyone at first very much accepted this and they said, yes, all motion requires an outside force. If something is moving, that is because something is making it move. There is some force that is making it move. Well, then someone came along and they said, but I have an issue. And the issue is a cannonball. Because they say you take a cannonball, you shoot it out of a cannon. And once the cannonball is in the air, it keeps moving. And they said, what keeps it moving in the air? why does the cannonball keep moving? Shouldn't there be some force that makes it move? They said it makes sense when you have, like, if you're talking about, like, I don't know, like a cart on the table, and you push a cart on the table and you have to keep pushing it in order to keep it moving. But they said, but what about when it's a cannonball in the air? Because the cannonball in the air keeps moving even though there's nothing to make it move. And so that felt very, very confusing to people. And they said, I don't know about this, Aristotle. But it was the widely accepted view that in order to make something move, there had to be some force that was making it move, until a fella came along by the name of Galileo. And Galileo said, well, actually, what if it takes no force to make something move? What if it takes a force to slow something down? And Galileo completely reframed the whole way that people had been viewing everything for all of time since Aristotle. So I guess that's not all of time. The way that people had been viewing everything since Aristotle. He said, okay, well, when the cannonball leaves the cannon, he says, it takes no force to keep it moving. It'll just keep on coasting without any force. He says if it's at rest, it takes a force to start it moving. He says once it's moving, it takes a force to stop it, but to keep something moving, that doesn't require any force. And in fact, if there is no outside force, it will keep moving at a constant speed in a straight line. Galileo said, let's suppose that we took that cannonball up into outer space, where there was very negligible amounts of gravity and no friction and no other forces. He said, in the absence of other forces, if I take that cannonball and I throw that cannonball will keep on coasting at a constant speed in a straight line forever. Galileo said, what if the way that things slow down is because a force acts on them? And this was the new idea. And Newton came along right after Galileo, and he wrote down Galileo's ideas, and he named them after himself. As you'll see, some scientists have a tendency to do. They just steal other people's ideas and then write down their own names. But Newton had this idea that Galileo had, and it wasn't really his idea, and so he wrote it down, and he called it a law. And he said, here's the law. The law is, an object at rest will stay at rest. It will keep on just being at rest. And an object in motion will actually keep moving until an outside force changes that motion. This is Newton's first law. Now here is one thing that I want to highlight for you here. And that is where Y. Sage Isaac Newton said, wait, oh, I want to change my color. Actually, not my size. Change the color. How do I change the color? I wonder if this will work as a highlighter or not. That is kind of my intention, but I kind of feel like it's not going to work that way. So anyway, we're going to try it, and we'll see what happens. I'm going to make it small just in case. Oh, wait. This is what I want. Wait, guys, this is about to be magical. Oh, wow, we're about to highlight. Oh, wow, for the first time in a Miss Wilson physics video, we are highlighting. Okay, here's what I want to highlight for you. Is I added these phrases here. At a constant speed. Ooh, that is a very light highlighter. Okay, well, we're going with it. It's going to work. Okay, at a constant speed in a straight line. Here's what we mean by at a constant speed in a straight line. If something is at a constant speed and it's not changing direction, we say that means that can be translated to mean, did I change my, no, my opaqueness is the same. That means that can be translated to mean constant velocity. In other words, an object will have a constant velocity unless it's acted on by an outside force. So, if that velocity is 5 meters per second south, it will keep going 5 meters per second south forever until some outside force changes it, either changes its speed or changes its direction. An object at rest stays at rest. Well, that's just an object with zero velocity. So an object with zero velocity will stay having zero velocity until an outside force acts on it. So we could really write Newton's first law as an object will have a constant velocity until an outside force changes it. Or an object will not accelerate without an outside force. These are all different ways of describing Newton's first law. Now, you have seen Newton's first law quite frequently in your life. Again, I'm going to make this big because I'm just going to talk for a second. You have seen Newton's first law quite frequently in your life, and I have a few examples for you. You know when you're in a car and someone is driving and they look up and they did not see that the red was coming, and so they slam on the brakes and you go, whoo, lurching forward. The reason why you go lurching forward is because you were an object in motion, and as an object in motion, you are trying to stay in motion. And so you try to keep going forward even though the car is stopping. And so you will continue to go forward at whatever speed the car was going at, because you will continue to move at a constant speed in a straight line unless there is some outside force that stops you. And this is why we wear a seatbelt, is because then the seatbelt is the outside force that stops you instead of the windshield being the outside force that stops you. You've also seen this before the other way, where if you're in a car and you're sitting still and then someone presses on the gas pedal really hard, or if you're on a roller coaster and they start accelerating really fast, you are sitting still on the roller coaster and all of a sudden they speed up really fast and you feel yourself get sucked back against the seat. Is that because the seat is suctioning you? No. It's because you are an object at rest. And as an object at rest, you are going to try to stay at rest. But then the seat starts moving, and the seat starts moving into you. So you stay at rest, but the seat pushes on you. And what you feel that feels like getting sucked into the seat, it's not really you getting sucked into the seat. It's the seat moving into you, and you are trying to stay where you are. You are an object at rest that tries to stay at rest. Here's another example. Next time you go to a restaurant where they pour some water into your glass and they pour some ice cubes into your glass, go ahead and take that cup full of ice water and give it a nice little spin like this. And watch your little ice cubes there. If you watch your little ice cubes in your little cup of water, you'll see that the ice cubes will stay right there as the whole glass rotates around it. Why? Because they're an object at rest. And that object at rest will stay at rest. You can do the same thing with your cereal bowl. Take your cereal bowl with your little cereal flakes floating in it. Go ahead and give it a nice spin. And you'll see that as you spin the cereal bowl, your little cereal flakes will stay right where they are. Why? They're an object at rest, and they'll stay at rest unless they're acted on by an outside force. You have also seen this anytime you have been asked, oh, I left my hammer out there. Okay, pretend, maybe I'll just go get my hammer. Okay, stay right where you are. Don't move, everyone. Stay. Okay, thank you for your patience. Okay, this hammer has two parts. You have the head of the hammer, and then you have the handle of the hammer. Now, what can happen to hammers sometimes is that hammers can go loosey-goosey. And when they go loose, what happens is the head starts to detach a little bit from the handle of the hammer. And this is slightly dangerous, as you could imagine, because if you're trying to swing this down to hit a nail, and the top part is a little bit loosey-goosey, well, that's a little bit dangerous of a situation as you're swinging something that is very heavy, that is loose. Now, what you can do is if your Uncle Larry asks you to tighten down a hammer, like if this top part, if the head of the hammer becomes a little loosey-goosey off the handle, what your Uncle Larry will say is all right, can you tighten down the hammer? And you'll say, oh, yeah. And if you try to tighten down the hammer by going like this, you'll have a very hard time. In fact, you'll end up just hurting your hand a little bit. And what you won't do is you also won't take the hammer, you won't hold it upside down and then bang it on a table like this. You won't do that either. What you'll do instead is you'll take a hammer like this, you'll hold it up like this, and you'll hit the end of the hammer on the table. Why do you hit the end of the hammer on the table? Well, because the head of the hammer, if you are swinging it down like this, and if you're trying to tighten it up, you swing it down like this. The head of the hammer is an object in motion, and that object in motion would like to stay in motion. So when it comes crashing down and it hits the table, well, the table stops the bottom, but the head is an object in motion, and it would like to stay in motion. So it will keep on moving down, and it'll close the little gap between the handle of the hammer and the head of the hammer. And that little gap will close, and it'll tighten down your hammer nice and good on there. This is Newton's first law. Newton's first law is often called the law of inertia. And let's change up our color here. That was kind of fun to write in yellow. We never write in yellow. Let's go with orange here. Newton's first law is often called the law of inertia, where inertia is the tendency of an object to keep doing what it's doing. Inertia is the tendency of an object to keep doing what it's doing. Inertia is the tendency of an object to keep doing what it's doing. That means it's the tendency of an object to stay at rest if it's at rest, or the tendency of an object to stay in motion if it's in motion. The tendency of an object to keep doing what it's doing. That's what inertia is. Now, not all objects have the same amount of inertia. We can measure an object's inertia based off of the mass of that object. The more mass an object has, the more inertia an object has. Here's an example. If you saw a small car, say something like a Toyota Camry, that is careening down the road, about to run into a baby gosling, and you want to save the day, then you could jump in front of that Toyota Camry and you could stop it, and that would be hard. But what would be harder is if you saw a semi-truck that was careening down the road about to hit a baby gosling and you desired to save the baby gosling. Well, then you would have to stand in the way of a semi-truck. And which one is worse? Standing in front of a Toyota Camry trying to stop a Toyota Camry, or standing in front of a semi-truck trying to stop a semi-truck? The second one. Because a semi-truck has more mass. So it has more inertia. And the more inertia something has, the greater its tendency to keep doing what it's doing. So, both a Toyota Camry and a semi-truck are both objects with mass. They're both objects with inertia. They both will stay at rest if they are at rest. They will both continue moving if they are moving at a constant speed in a straight line. However, the semi-truck, because it has more mass, it has a greater tendency to keep doing what it's doing. In other words, it's harder to change the motion of something with more mass, and it's easier to change the motion of something with less mass. Here's an example. Suppose that you got to the airport and they said, hey, you actually get to choose which plane you want. You can either take this little teeny tiny plane that has enough space for you and the pilot and the co-pilot and a dog, or you could take this big plane that we use for international flights. Which one would give you a less bumpy ride? You say the big plane, the one that they would take for international flights. Why? Because it has more mass, and so it has more inertia. When the little plane is flying and it goes over a little weird pocket of air, then that little plane will go over the weird pocket of air. Why? Because it's small. It does not have a lot of mass, and so it's much easier to change its motion. It has a lesser tendency to keep doing what it's doing. So if it goes over a weird pocket of air, that little plane will over the weird pocket of air. But if you have a giant plane, like one of those international planes with tons and tons and tons of rows, it's an enormous plane. If you have a giant plane, and that giant plane is pummeling through the air, and it hits a weird pocket of air, it'll just go and go straight on through. Why? Because it has more inertia. It has a lesser tendency to change its motion. So if it is moving in a constant speed at a straight line, it has a tendency to keep doing that. And its tendency to keep doing that, its inertia, is bigger than the inertia of the little plane. The last thing that we're going to talk about today is a small example here that is from the Paul Hewitt video that I want to show you. So I'm going to draw a little picture of this scenario. Here's the scenario, is that Mr. Hewitt has a steel ball, and that steel ball is tied by two strings. There's one string on the top holding up the string ball, and holding up the steel ball, and another string on the bottom hanging off the steel ball. So it kind of looks something like this. I'll draw you a picture, and of course we'll change our color to blue, obviously. And here's what the setup looks like. You have a steel ball like this. And then you have on the top, it's tied to a string, and on the bottom, you also have a string tied to it like this. And then this top string is attached to a little rod here, so that the steel ball is hanging from the top string like this. Now here's what Mr. Paul Hewitt does. Is he says, okay, I'm going to do two demonstrations. He says, the first demonstration that I'm going to do is I'm going to take the bottom string and I'm going to pull on it very, very slowly. And he asked the class, which string is going to break when I pull on it very, very slowly? The top string or the bottom string? And then he says, the next thing that I'm going to do is I'm going to pull on that bottom string really, really fast. And which string will break, the top string or the bottom string? And that is the question that he asks his students. I'm going to quick pause the video here, and then after we take a quick pause, we'll come back and we'll answer these two questions. Which string breaks when you pull it slowly, the top string or the bottom string, and which string breaks when you pull it fast, the top string or the bottom string? Okay, take a second, think about it. Okay, so when Mr. Hewitt pulls on the string, and when he pulls on it very slowly, the top string breaks. And let's talk about the reason why the top string breaks. Well, first, do you agree that between these two strings, if the ball is being held up here by this top string, then before Mr. Hewitt touches anything, this string is already under stress because it's already being pulled down by the weight of the ball. Then, when he starts to pull, looking at this bottom string before he starts to pull on it, this bottom string here is just kind of hanging out. It's just kind of having a good time. There's not really a lot of tension here before he starts to pull on it. It's just being his little self. It has nothing to carry. When he starts to pull on the string, though, he adds an additional tension into this string, so now this string is stressed, and that tension goes all the way up to this string as well. So now the top string, which was already stressed, is stressed by the weight of the ball pulling down, but it's also stressed by the weight of Mr. Hewitt pulling down on the whole thing. And so this top string here will break, and the bottom one will stay in contact. Stay together. It'll be one string. Okay. Let's now look at what happens when he pulls on it very quickly. When Mr. Hewitt comes along and he grabs a hold of that bottom string and he pulls it very quickly, the bottom string breaks. Let's talk about why. Here's the situation. When you look at this steel ball has weight, but it also has a lot of mass, meaning it has a lot of inertia, which is the tendency to keep doing what it's doing. When he pulls it very quickly, he says, "Hey, steel ball, would you like to accelerate very, very fast to change your motion a lot?" And the steel ball says, "No, thank you. I am actually an inertial object, and as an inertial object, I do not like change. I'm an object at rest, and I much prefer to stay at rest. Thank you very much." And you say, "No, but do accelerate." And the ball says, "No, thank you." The string, meanwhile, says, "I'm a string, and I am fairly light. I have fairly little mass, and so my inertia is really not all that significant." And so if you say, "Hey, string, change your motion a lot," well, it has less inertia. It has a lesser tendency to remain doing what it's doing. And so if you say, "Hey, experience a great acceleration, start moving really fast," the string here says, "Okay, I can go along with that." And so the string will go along with that, but the big steel ball here won't go along with that. And so the steel ball will stay in place and this bottom string will break. Because the steel ball stays in place, then this top string is protected, because if it were to break here, then the steel ball would also move, and the steel ball refuses to move. The steel ball will stay in place. This differentiates really nicely between weight versus inertia, which we will talk more about in our next lesson, like tomorrow, or in our next YouTube video. This example here shows us that something is true, that it doesn't just matter how much inertia something has, it also matters how much you're asking something to accelerate. If you ask something to accelerate a lot, and it has a lot of inertia, it will say, "No way, Jose," and it will not go through with that acceleration. But if you ask something to accelerate a little bit, it's more likely to go through with that acceleration. If you just say, "Hey, don't change your motion a lot. Don't go from rest to really, really fast, but go from rest to just a little bit of motion." Take the roll of paper towels, for example. If you have a roll of paper towels and you need to get a paper towel, you have a few options. First, one thing that you could do is you could set down whatever you're holding at the moment. You could put one hand on the top of the roll of paper towels, take the other hand, and tear off very slowly one piece of paper towel. And then you would have one paper towel separate from the rest of the roll. Or you try this. When you get home, go up to your roll of paper towels. And, I want to make this. Let's move it out a little bit. Go up to your roll of paper towels. Grab onto that one paper towel and whip it down real quick. the whole roll of paper towels, which has a lot of mass and a lot of inertia, the whole roll will say, excuse me, I am not accelerating, thank you very much. I am an object at rest, and I would like very much to stay at rest, and so that is what I will do. But the one paper towel says, I'll go along with that. And the one paper towel will accelerate, leaving the rest of the paper towel roll behind. And you can get one paper towel off the roll if you just go and move really, really quickly. Here's the main idea, is that if you are changing the state of motion of an object, if you are applying an outside force, it doesn't matter only about how much inertia an object has, but it also matters how much you are asking it to change its motion. Ask it to change its motion just a little bit, and that'll be all right. It'll be willing to go along with that. But ask it to change its motion a lot, and that is a lot tougher. You're going to need a much bigger force to accomplish that task. And that is pretty much all for today, folks. Today we talked a little bit about inertia. We talked about Newton's first law. We learned that Newton's first law says that an object in motion will stay in motion at a constant speed in a straight line. It also says that an object at rest will stay at rest. All of that is true unless acted on by an outside force. An outside force is what causes a change in motion. Otherwise, motion will keep on going the way that it is. We talked about some applications of this, and then we talked about the concept of inertia, that some objects have a greater tendency to keep on doing what they're doing than others. Then, lastly, we talked about how if you are changing the motion of something, it depends on how much you're changing it, whether or not that object will actually stay at rest, quote unquote, or stay in motion based on how much you're trying to change the motion of the object. It requires more force to change the motion of the object more. And if you don't have enough force to change the object, to change the motion of the object, then it'll keep on doing exactly what it's doing. And that is pretty much all for today, folks. I hope you have a wonderful rest of your day. And I'll see you all in the next video. Bye, good people.